All right, I made it. If my calculations are correct, I just arrived at the beginning of the second video on the heat equation. I've been on a closed timeline curve, time traveling to try to avoid a catastrophe. So if everything worked all right, what you have experienced is the end of the previous video, and then you expect here to see two examples in a new video. I really hope that that's what happened and the structure of the space-time continuum is repaired, and enjoy the video. Okay, I'll leave you with myself. All right, so here's another example of the heat equation, but it's a slightly more difficult example. What changed? Well, I changed several things. In the boundary conditions, I put one of the sites at temperature 10. So now the temperatures are not 0. And that makes the problem more difficult, all right? Because all that we applied before worked nicely because the boundary conditions were 0. Now, when we have different boundary conditions are not different from 0, some different from 0, then the problem we need to be a little bit ingenious in order to solve it. Now, you see that the initial condition has also been modified. Well, you see, because this initial condition, if I don't add this here, I will not be compatible with the boundary condition. The initial condition has to be compatible with the boundary condition. So you see, when u00 has to be 0, so u00 is still 0, and utl has to be 10. The initial condition is for t equals to 0, but u of tl has to be 10, always for all t. So independently of that, when x is equal to L, I need the function to have the value L for all times. So in particular, for t equal to 0 also has to have the value 10. If I don't add t over L times x, that doesn't have the value 10. Okay, so I modify the initial condition. Okay, that's not something you need to know. You're given an initial condition and better be compatible with the boundary condition that you have. Okay. All right. So how do we solve that? Now, the one thing that we realize first is that this is a linear equation and the superposition principle applies. So I know that I can write the general solution to the homogeneous problem, and then I can add a particular solution to the non-homogeneous problem. In this case, the non-homogeneous problem is having a non-homogeneous boundary condition. Now, slightly different than the superposition principle plus the solution to the non-homogeneous equation that we saw before, but fundamentally the same kind of thing. Let's see what I'm going to do in a more schematic kind of way. I'm going to decompose the problem. This is the solution to the full problem. I'm going to decompose it into two problems, two subproblems. One, the homogeneous problem, in which I solve the wave equation for the heat equation for UH equals kappa second derivative U respect to x squared. Homogeneous. And homogeneous means that I want it to satisfy the homogeneous boundary conditions. So I want this to be the same problem as we had before. Of t of 0x, of t0 equals 0, and the same for UH of TL. So you see, this is without imposing the initial condition. We impose the initial condition at the end. This is just to impose the boundary condition. So first, the homogeneous problem that satisfies that, and then I'm gonna add a solution to if you want a particular solution, UX, that I'm gonna put the burden of satisfying the non-homogeneous part on it. So again, it has to be a solution to the heat equation, otherwise the sum would not be a solution. X squared. A particular solution of this, but now the boundary conditions for 0, yes, it's 0 is the same, but the non-homogeneous one, I'm going to assign it to this guy. All right. There you go. A particular solution to the heat equation that satisfies the boundary condition that is not homogeneous. Is that okay? Let's check. Okay, so the total U has certainly to satisfy the total boundary condition. So let's see what happens. U of T0 is equal to UH of T0 plus UX of t 0 and u of tl is equal to uh of tl plus uec of tl. All right, this one is 0, this one is 0. So wonderful, u of t0 is 0, it satisfies it. What about this one? Well, this one is 0 and this one is 10. Oh, wonderful, so its total is 10, so it satisfies the boundary conditions. You see? So if I have the general solution to the homogeneous problem that captures all the dimensionality, here is the sum of all the eigenvectors of all the vectors of the space of solutions, so sum of on a basis of the vectors of the space of solutions. So it's the general solution to the homogeneous problem. And I add just one particular solution that the only mission of that solution is to take care of the non-homogeneity. Similar to what we did when we solved ODEs with inhomogeneities in the equation. All right? Wonderful. And you see how, if I do that, the total solution satisfies the boundary conditions. Now, if I also, here's the reason, you see, like, let's just write it. So, what do I want? That will work probably. What do I want? Well, a solution of the heat equation, which is equation 1 in there, satisfying BCs and initial conditions given by boundary conditions BC and initial condition IC. Satisfying those boundary conditions and initial conditions. Okay, that's what I want. That's my objective. All right. Now, if I get, so is UH and UEC are solutions of 1. That means that U equals UH plus UEC are solutions of 1. Wonderful. Then UEC satisfies the boundary conditions. UH does not. But U equals UH plus UEC satisfies the boundary conditions. Why? Because UH doesn't, but satisfies that the conditions are 0 exactly. So if this satisfies it and this one gives you zeros, well, the total satisfies it. Wonderful. So far I have U equals UH plus UEC is solution of 1. Check. Satisfies BCs. Check. So what do I do now? Impose at the end, impose IC on U and find the particular solution. So you see, the logic works. This solving, decomposing the problem into 2 sub-problems gives me what I want. I want a solution of 1 satisfying these 2. And I do that by combining a solution that does not satisfy the BCs, but gives me a generality of writing things in terms of Fourier series as we did before, plus a solution that satisfies the boundary condition, but it's simple. Now, that gives me the combination of the 2, the linear combination of the 2 are solutions that satisfy the BCs. All that I need to do is impose the IC on the sum of the 2, and that will give me the final solution. All right, so let's get with it. So I just need to find one particular solution that does that. I need to find the simplest possible solution. All right, let's do it. All right, so we're going to first find UEC. So the problem I want is UEC that satisfies that T0 is equal to 0, and UEC of TL it's equal to 10. Now, there are 2 ways of doing that, the systematic way and being a bit clever about it. Let's do the systematic one. I just need to find one solution, so hopefully the simplest possible. Let's see if there is any solution with lambda equals, from case 1, lambda equals 0. So remember, we have case 1, which is lambda equals 0, and that means that, as we have lambda equals 0 in here, we get that the roots m is equal to 0 double. With a 0 double root, we know that the solution, at least the x part, is equal to ax plus b. And we also know that the t in that case is just 1. All right, so very simple. We impose those and we say U equilibrium in this case. If it's case 1, if there's any solutions in case 1, U equilibrium of Tx is equal to Ax plus B. Let's impose the conditions then. U of T comma 0 is 0. That means that A times 0 plus B equals 0, which means that B is equal to 0. The other condition, UX TL equals 10, not 0. Alright, so that means that A times L plus B equals 10. But I also know that B is 0. Because B is 0, that means that AL is equal to 10, and therefore A is equal to 10 over L. Well, look at that. We have a solution here. Wonderful. So that means that UX is actually UX from this, all right? UX of Tx is actually a function of only x, so let me write UX of x, it's equal to 10 over Lx. I found my particular solution. Wonderful. I don't need to go to the other cases because for UX, unlike for this one that I want the general solution, for this one I just need one particular solution, and that does it. Amazing. All right, so that is the systematic way of finding it. There's a simpler way of finding it, which is doing a little bit of physics, which is saying, right, I know that the homogeneous problem, whatever it is, what happens, remember what it was, the homogeneous problem. The temperatures were 0. It means that all the temperatures will eventually fall all of them to 0 in infinite time. The solutions are exponentially suppressed. This is physics, doing a little bit of physics reasoning, okay? Right, so that means that if the homogeneous solution will definitely decay to 0 at the end, for infinite time, when time goes to infinity, right, we get an equilibrium solution. The thing doesn't evolve, reaches equilibrium eventually. That equilibrium solution has to still satisfy the boundary conditions. That's why it's called equilibrium solution. It's the solution at t going to infinity. So what happens at equilibrium? Like, you know, for long times, t going to infinity, oops, the system reaches equilibrium. All right, and what does that mean? Well, that means no longer depends on time. It's stationary, right? Because if it's at equilibrium, the thing doesn't evolve in time anymore. Well, if that's the case, I know that partial u, partial t will be 0 in the equilibrium regime, and therefore 1 gives me 0 equals kappa second derivative of u with respect to x equals 0. All right, then I can divide by kappa, kappa disappears, and I get just u of x, u equilibrium of only x dot dot equals 0. If you integrate twice, you get that this is equal u equilibrium of x is equal to ax plus b, right? If you take the second derivative of that, you get 0. And then you impose the condition same as we did here, right? And then you get again the same thing, that then is equal to 10 over L. Either way works. That's the one that you would find in textbooks usually. That's the systematic one using the method that we learned, okay? All right, now that we've done this, let's solve the whole problem, shall we? So we're gonna recall, now we solved the equilibrium solution already. We need to solve the homogeneous problem. The homogeneous problem, now we know how to solve it already, right? Because we've done it once, so I'll do it a little bit faster. Okay, so let's erase the board. All right, so for the U homogeneous, which is this problem here, we know that we have several cases in the separation of variables. We have case 1, lambda equals 0, but then we have homogeneous boundary conditions, and we know that for lambda equals 0, of course, m is equal to 0, and U homogeneous of Tx has to be Ax plus b. But then this is incompatible with the homogeneous boundary conditions, and we see that very easily because U homogeneous of T0 is 0, U homogeneous of TL is 0, and this would mean A times 0 plus B equals 0, which means B equals 0, and this one is A times L plus B equals 0. Since B is 0, so this means B is equal to 0, and applying that, I get that A is also equal to 0, so incompatible with the initial condition. That's the trivial solution, right? We've done that already, so that's why it went so fast. We also have the case lambda equals 1, in which case, lambda larger than 0, in which case I call lambda is equal to omega squared, all right? And in that case, we had that U homogeneous Tx was A e to the omega, right? A e to the omega x plus b to the e to the minus omega x, okay? Because remember, m in this case is plus minus omega, all right? And if we impose the boundary conditions on this, the homogeneous boundary conditions, Tx, so T0 equals 0, that means A times e to the 0, which is 1, plus b e to the 0, which is 1, equals 0, that means A equals minus b. On the other hand, imposing UH of TL equals 0 gives me e to the e omega L plus b e to the minus omega L equals 0. Now using that A is equal to minus b, that gives me A to the e omega L minus e to the minus omega L equals 0. And we found, well, this is the sinh of omega L. So three options we have here, right? We have, well, two options first, if you want to nest it like that. Option 1, A equals 0, but then B is equal to 0, which is the trivial solution, also incompatible. It's the same as before. The other option, let's put it here, is that the sinh, I'll do it like that, yeah. The sinh of omega L equals 0. But the only possibility for that is that omega L is equal to 0. So either omega is equal to 0, which is not only incompatible but inconsistent, because we're in the case that lambda is greater than 0, what we call case 2. The other option is L is equal to 0, which is incompatible with our problem. Incompatible. So I'll just do like that. Okay? That we knew because we've done it before. This is just a repetition. Let's take case 3, which is the one that gave me the solutions. And then case 3, case lambda less than 0, then we call lambda is equal minus omega squared. In that case, we get that U homogeneous Tx, it's equal to A cosine omega t plus B sine omega t. All right? And now, remember what we found. There are many solutions. Let's find that again, okay? If we impose the boundary conditions here, we get that UH of T0 is 0. Well, that means that A cosine of 0 plus B sine of 0 equals 0, which means that A times 1 equals 0, so that means A equals 0, all right? And now, what we get is UH of TL equals 0, again, the homogeneous boundary conditions for the homogeneous problem, and then we get, let's apply already that A is equal to 0, so we get B sine omega L, that's right, equal to 0. All right, so two options. B equals to 0, that with A equals to 0 gives the trivial solution, which is incompatible. And the other option is that the sine of omega L is equal to 0. But that gives me two options, right? L equals to 0, incompatible. And then it gives me the eigenvalues. By the way, I keep calling them eigenvalues. Gives me an infinite number of eigenvalues. Values of omega, let me call it omega equals, let me call it omega sub n equals n pi over L, for n being an integer. All right, wonderful. So that gives me an infinite number of solutions. Let's write the infinite number of solutions. U homogeneous n, because there's an infinite number of them. Tx is the x part that we just solved. The x part here is a sum of a cosine and a sine, but not a cosine because a is 0, so just a sine. B, but I have to call it Bn because it's a different constant per solution, because I found many solutions with different omegas. Sine of the omega n, which is n pi over L x, right? And that multiplies the t solution, because you remember, the solution is the product of the two. So the t solution here is e to lambda. Lambda is omega squared, so it's n pi squared over L squared kappa t. But of course, these are an infinite set of solutions. I need to, for the general solution, I need to consider all of them. So if I consider all of them, I get that the homogeneous solution, the total homogeneous solution, Tx, is the sum of all the n independent solutions for the system, the sum of all the elements of the base of solutions, is sum n equals 1 to infinity of Bn sine n pi over Lx exponential of minus, because remember, lambda is minus omega squared, n squared pi squared divided by L squared kappa t. All right, so now I can write the general solution to the total problem, which is u of Tx, the sum of the homogeneous, the solution to the homogeneous problem, the general solution to the homogeneous problem, n equals 1 to infinity, Bn sine of n pi over Lx exponential of minus n squared pi squared divided by L squared kappa t, plus the particular solution to the inhomogeneous problem, the equilibrium solution, 10 over L times x. The last step is determining the value of the constants Bn, and we know how. We determine that value according to the initial conditions. So now, on this one, impose, so let me separate this, right? Impose the initial condition that tells me that u of 0x equals f of x. All right? That means that on the one hand, I write u of 0x, which is substitute x t by 0 here, which gives me a 1 in here, there's no other t's. That gives me sum n equals 1 to infinity Bn sine n pi over L x plus 10 L x equals f of x. All right, so this is a Fourier series indeed, but the Fourier series, I need to put this on the right hand side. So I know that means that f of x minus 10 over Lx, it's equal to n equals 1 to infinity Bn sine n pi over L x. So Bn's are the coefficients of the sine Fourier series of the function of the odd extension of f of x minus 10 L over x. So if you want to write it as an integral, Bn would be equal to 2 over L. Remember, it would be 2 over 2L, but twice. Remember what we did before is the odd extension, okay? Integral from 0 to L. You know it's minus L to L for being the odd extension, but a factor of 2 because it's minus L to make it 0 to L. All right? Then we get dx of f of x minus 10 over L x times the sine of n pi over Lx. And then you put there your function and compute those coefficients. Now in this case it's very simple because the solution is the same as before. If you substitute f of x by this, then you realize that the 10L over x cancels and we get the same result as we had before. In our case, by inspection, we get the cosine. Remember that this thing is 1/2 the sine of 4 pi over Lx, right? So by inspection, we got here this 1/2 of the sine of 4 pi over Lx, all right, plus 10L over x minus 10L over x equals this sum right? And then we see this cancels, and by inspection, the only term in this sum that survives is b equals 4 because that has a sign of 4 pi over L. No other term has the 4 pi over L. So we find by inspection, let me do it over there perhaps. Let's do it there. All right, so I open a wormhole there and here. So by inspection, we see that b4 is equal to 1/2 and bn different from 4 is 0. So the solution to the whole problem after imposing all the conditions is the following: is u of tx it's equal to let's just write 1/2 of the sine of n is equal to 4, so 4 pi over Lx. Now the function of time, which is e to the minus n squared, which is minus 16 pi squared divided by L squared, kappa t, and then plus 10 over Lx, and that is the solution. And by the way, you see that in equilibrium after the temperature profile is dissipated, what you get is an increasing temperature as you move to the right. Makes sense. Something hot here, something cold here, temperature in the middle follows a straight line between the two. All right, I hope that this wasn't too confusing. If it was, please bring questions over to our review session. But again, if you have any inhomogeneous boundary conditions, put the burden on solve the problem as you know how to solve it homogeneously, and put all the burden of satisfying the boundary condition on a particular solution to the non-homogeneous problem. And that allows you to find a very simple solution, not here because I erased it already. It came from case 1, if you remember. So very simple solution. And then when you found that solution, then find the general solution to the homogeneous problem and impose the boundary condition on the total solution. All right, let's see one more example and we're done with this equation, at least for now. All right, let's do a more complicated example. This is as complicated as it gets. We're gonna see the example of what happens when I get a bar that has some temperature. I heated it non-uniformly, so I have a distribution of temperature, and then I bend it and I make a ring out of it. How is heat transmitted in the ring? Let's see. So I have here a bar of length 2L, just for nice symmetry and simplicity, I made it 2L. And what I do is I have a profile of temperature, so there's a profile at time 0, there's a profile of temperature, and I get the bar and I bend it like that, so that on the right I get x equals L. I identify the 2 points, x equals L becomes the same point at x equals minus L. All right, wonderful. So what are the boundary conditions here? Well, the boundary conditions are that I put it on ice, I put it on itself. I identify the 2 points, so I say that the temperature at the point minus L, it's equal at the point L, and the same here, minus L to L. So the temperature on the two extremes of the ring are the same because it's the same point, all right? And then the derivative of the temperature at that point has to be the same as well because it's the same point. I mean the identification. That's what happens. That's the mathematical description of making a perfect thermal contact between the two, all right, with the ring. Wonderful. So now we do as we did before. We apply, let's just recap what we did, because this is something that needs to be ingrained in your brain, because when you solve exercises, I want you to show me this process. I want to solve this equation. First, ansatz. Let's see if the solutions are of the form some function of time times some function of position. If I assume this and I plug it into the equation 1, then I get this equality without the lambda in there. X dot over x equals 1 over kappa t dot over t. And then we realize, oh, the function on the left is exclusively a function of x. The function on the right is exclusively a function of t. And they are equal for all values of x and t. That can only mean that neither of them depend or on x or on t. So they have to be a constant. That's the separation constant. And the allowed values for that separation constant is what we call the eigenvalues of the problem. All right, for reasons. Okay, right. But that also means that I have two equations. I have this equation on this side, the equation that I'm showing right now, which is the first line, and this equation on the other side, which is the equation that I show here. Very simple equations. This one is first order, linear, but it's also separable. And I solve it, this is the solution. This one is a second order linear ODE of constant coefficients that I know how to solve, characteristic polynomial. And depending on the roots, it would be either, a polynomial times an exponential or a sum of exponentials or sine and cosine. Okay? All right. Wonderful. So let's start from case 1, from the simple one. All right? So case 1 is when lambda is equal to 0. That means that n is equal to 0 double. We have a double root. So that we know in that case that the solution, super important, right? I impose it, so every time when I impose a condition on, if I say u of t minus l equals u of t l, because this is the product of x of l and t of t equals x of, minus l here, x of l, t of t, of course I can cross this out. So having a condition on the u's for the same t means I have the condition for the x's, all right? That's why I always equate the x's. All right, actually in case 1, t is even 1 because lambda is 0, but for the others, right? Because this is a question that sometimes I have. Same goes with the derivative, because the derivative with respect to x is just a dot in here. The t doesn't notice, so again, it cancels. All right, that's a little note. Let's write what the solution is like in the case 1. Case 1, we know what the solution is like. It's just bx plus a. And you may be wondering, but in the past you call it ax plus b. Yeah, calling it bx plus a is more clear for this exercise. In fact, it's better. The reason I didn't care too much before is because it wasn't that important. But again, those are constants, so emphasizes also that I can call the constant Joshua if I want. All right? This is just clear from what we're going to do. All right, this is x of x. And t of t is 1 in this case. All right? Let's compute the derivative because we need it for the second condition. X dot of x is equal to just b. All right, so let's impose the boundary conditions. First condition tells me u of t minus l is equal to u of t comma l. All right, so that means that b times minus l plus a it's equal to b l plus a. The a is cancelled, the l is cancelled, so what I get here is that b is equal to minus b. Aha, well that means that b is 0. There's no b in this problem. All right, let's impose the other condition. The other condition is not going to tell me much, as you will see. Ux of t comma minus l equals ux of t comma l. That tells me that on the left hand side b, on the right hand side b equals b. Tautology doesn't give me, tautology gives me no information. So all the information that I got from here is that b is equal to 0. So the only restriction that the boundary conditions impose on case 1 is that b is equal to 0. So unlike the previous cases, in this case we get a solution from case 1. We get that x of x is equal to a constant, but because it could be any constant, let me call it x0 because it comes from the case lambda equals 0. That means that I get a u tx z0 comes from the case lambda equals 0, which is equal to just a0. All right. So we have a solution from case 1. We cannot throw it out. So let's write this solution here to store it. u0 of tx is equal to a0, and we need to definitely add it, this solution. Okay. Wonderful. Let's move to case 2. We got one solution. Let's see if there are more solutions in other cases. Pretty sure there will be, because a ring is not just as boring as having a constant temperature everywhere. That's what will happen in the end. They will reach a constant temperature everywhere, right? That's why it's the stationary, the equilibrium solution. Equilibrium solution comes from this case always, because that's when time dependence disappears. When lambda is 0, T of t is a constant. All right, let's see the case 2. All right, in case 2, we remember that we have that when lambda is larger than 0, then we call lambda omega squared, and there are two real roots, plus or minus lambda. When that's the case, we remember that the solution is of the form, in this case, x of x is equal to e to a e omega l plus b e to minus omega x b minus e to the minus omega x, right? The positive exponential with the first eigenvalue plus omega, the second eigenvalue minus omega. Now, the problem that we have here is that to apply these conditions is much more convenient to write this in a different way. We can write this as a tilde, a different constant, but still arbitrary, cosine, cosh of omega x plus b tilde sinh of omega x. Why can we do that? Well, remember that the hyperbolic cosine is e to the x plus hyperbolic cosine of x is e to the x plus e to the minus x divided by 2, and the hyperbolic sine of x is e to the x minus e to the minus x divided by 2. Now, that means that if you substitute this here and here, you get the dependence, right? I mean, to get group together all the e to the omega x, group together all to the e to the minus omega x, and you will find two equations that relate a tilde and b tilde with a and b. And because they are arbitrary constant, I can always do it. As an exercise, find the relationship between the a tildes and b tildes and the a and b's, okay? It's not difficult, and we actually did it for the sine and the cosine in the past. So, it's the same way that when we have a e to the I omega t plus b e to the minus I omega t with arbitrary constants, this is the same as some constant, the cosine of omega t plus b tilde the sine of omega t. Alright, so it's just a different way, more convenient for this case. They're both correct, just imposing the conditions is much easier if you write this solution in terms of cosh and sinh. Alright, if you have any questions, try to relate the two. Find the values of a tilde and b tilde as a function of a and b. And because they're arbitrary constant, you can always write it like that. If you have questions or you have problems with that, ask me in the review sessions. Alright? Okay, let's clean up the board and let's impose the boundary conditions. To impose the boundary conditions, we first need to find the derivative. So let me write here, this is x of x. Let me write here x dot of x. It's pretty easy. The derivative of the cosh is the sinh. So it's omega sinh omega x plus, and the derivative of the sinh is the cosh. And there we go. No different sign this time. It's not like the trigonometric ones. Wonderful. So let's impose the first boundary condition. The first boundary condition tells me that u of t minus L is equal to u of t L. Alright, so this implies that a tilde cosh of minus omega L plus b tilde sinh of minus omega L has to be equal to a tilde cosh omega L plus b tilde sinh omega L. Now what we use is the parity of the two functions. Let's draw them. So the cosh, remember, is ex plus e minus x divided by 2. We plot the cosh, we get that for x positive, this doesn't dominate, this dominates, right? So we get at x equals 0, this is 1, right? Well, 1/2 because divided by 2. So this is 1/2. And as x grows, it goes exponential. And this one also goes exponential in the same way. So it's an even function. Now the sinh, let's write it here. The sinh is a minus in here. We plotted it before, so the sinh at x equals 0 is 0, and for positive x, this dominates, grows exponentially. Oops. I don't know why it's not. Okay. Grows exponentially. And on the other side, this one dominates and grows exponentially to the negatives. So it's an odd function. So the sinh is an odd function, and the cosine, let me just write it here, cos of minus x equals the cos of x, whereas the sinh of minus x equals the minus sinh of x. All right, let's erase the plots. All right, so now using the properties that the hyperbolic cosine the sine is even and the hyperbolic sine is odd, we can write this again as, just right below, this is a cos of omega L, LT A tilde, plus, or minus, sorry, b sinh of omega L equals to a cos of omega L plus b sinh of omega L. This one cancels that one, and what we get here from this equation is that, right, 2b sinh omega L equals 0. So we have two options. Either b is equal to 0, or well, option 1, let's say, the sinh it's omega L is equal to 0, but that implies that omega L, because remember that's the only 0 of the function, omega L is equal to 0, but that implies that either L is equal to 0 or omega is equal to 0. This one is inconsistent. We are in the case that lambda is greater than 0, so omega squared is greater than 0, cannot be. And this one is inconsistent, incompatible. This one is inconsistent, this one is incompatible. That's not compatible with the fact that we have a finite extension. Alright, so the other option is that b is equal to 0. So that's the one we have to take. Wonderful. That simplifies the equations a bit. Let's impose the boundary condition as the second one. The second boundary condition tells me that ux of t minus L is equal to u of TL. X derivatives, alright? So that means that x dot of x of minus L has to be equal to x dot of L. That means that a omega sinh of minus a tilde, of course, minus omega L. Also, I magically wrote the tildes on the b's that I forgot in the previous step. Sorry about that. It's corrected, of course, it's b tilde. Now, I would have to write b tilde omega cos, but I'm not gonna, because I already found that b tilde has to be 0. So to save a little bit of writing, I'm gonna just impose that b is 0 because that's the only compatible solution for b that we have. So this has to be equal then, if there's no b, to a omega sinh of omega L. Same as before, the sinh is an odd function, so I can do the following. Look at here. So this, I took the sign out, and that means that twice a omega sinh, right, sinh omega L equals 0. Wonderful. So options that we have for that, well, either a tilde equals 0, or omega equals 0, or the sinh of omega L equals 0. Now this one we already discarded. This one is also discarded, is the inconsistent one. So the only possibility is that a tilde is equal to 0. So the only solution that we have is a tilde equals b tilde equals 0, which is the trivial solution, which is incompatible with having some temperature, some distribution f of x of temperature initially, unless it's 0, okay? All right, so this is case 2 that I never wrote. Sorry about that. Case 2 doesn't give us any non-trivial solutions. Let's check case 3. Case 3 is the possibility that lambda is less than 0. And then we call lambda minus omega squared. All right. We know in that case we have two complex conjugate roots. And the solution then is a combination of sines and cosines. It's a cosine omega x plus b sine omega x. I also computed the derivative here because we need it for the conditions, which is minus a omega sine, right? The derivative of the cosine is the minus sine, plus b omega cos, the derivative of the sine is the cos. Now, let's apply the boundary conditions. The periodic condition on the function gives me that, of course, x of minus L has to be equal to x of L. That tells me that a cosine of minus omega L plus b sine of minus omega L has to be equal to a cosine omega L plus b sine omega L. Alright, so we realized quickly that the cosine is an even function, the sine is an odd function. So we can do one by one. First this, second this, and third, well, there's no third. Third, just we cancel this and this because it's the same. So we get that 2b sine omega L equals 0. And that's pretty interesting because in this case, yeah, we have that maybe b is equal to 0, but maybe it's the sine of omega L equals 0. And the two of them are valid in this case. Okay, let's explore the other condition and see what it gives us. The other condition tells me that u derivative TL minus L equals u derivative TL. So again, that means x dot minus L equals x dot L. Alright, so that means that minus a omega sine minus omega L plus b omega cosine of minus omega L is equal to minus a omega sine omega L plus b omega cosine omega L. Right, let's use parity again. The sine is an odd function, therefore we get that. The cosine is even, so this is simple. We just need to vanish the sine. And that means that what we have here is this one cancels, and look at this now. We get that 2a sine omega L equals 0. This is super interesting because that means that either a is 0 or the sine omega L is 0. And you see, this is extremely interesting because we can have that one of them is 0, but the other one doesn't have to be 0 if the sine is 0, and vice versa. So we get solutions from both of them. Let's just write them. Let's just recall what we have here. All right. So first of all, let's consider the possible cases that we have. We have a case where from the first one, I can pick and choose one of each. One from here and one from here. So let's say, first we have possibilities. Let's write the possibilities. Possibility 1, I take b equals 0, a equals 0. That's possible. That makes, I satisfy the first condition and the second, regardless of what the sign is. Yeah, sure, but that gives me the trivial solution. Trivial solution, which is u of t x equals 0. All right, that's about possibility. Possibility 2, sine of, so b is 0, but a is different from 0. Well, if you choose that one, then b is 0. Satisfies this immediately, but this one is not satisfied unless the sine is also 0. So in this case, we need that the sine of omega L is 0. The other option is that a is 0 and b is the one that's different from 0. Well, if we take that one, then we get that also we need the sine of omega L to be 0. Okay? And you can tell me, yeah, you could do both at the same time. Neither of them are 0 and make the sine equal to 0. Yeah, that's fine. But they're independent solutions, right? You see, because I can do this one and this one and this one, and I can combine the two. One of them gives me the cosine-like solutions, the other one gives me the sine-like solutions. So I combine them like this, the case where neither b or a are 0 are already included in the linear combination of the cases where a is not 0 plus the cases where b is not 0. All right? Hope that makes sense. If not, please do ask questions about it in the review section. Wonderful. So the sine of omega L equals 0 means that again, omega L has to be a multiple of n pi, where n is an integer. So that means that omega is equal to n pi divided by 2, by L. All right? Wonderful. So that means that there's an infinite number of eigenvalues, let's call it omega n, and that gives me an infinite number of solutions. An infinite number of solutions here, and an infinite number of solutions here. Let's write them both. Let me clear up the board a little bit. I'm going to erase the derivation of these conditions. All right, so we have that omega is n pi over L. Let's get the case a equals 0, b different from 0. But in this case, let me call the solutions, so the solutions xn of x, let me call them with b in here, because they have a b different from 0. So they are of the form b sine of n pi over L x. And that means that the total solution for those ones, the possible solutions with different eigenvalues, un, let's call it super b, un b tx. By the way, I need a subindex n on the b, every constant is different. Now we write all the possible solutions in this family, a equals 0, b different from 0, which are I call u sub n b, and those are the xn times the tn, which is b n sine n pi over L x, times e, and omega is minus omega squared, lambda is minus omega squared, so minus n squared pi squared divided by L squared, and then kappa t. Alrighty. And we also get another infinite set of solutions from the case where a is different from 0 and b it's equal to 0. And then we get, let's call this xa, xan are the an cosine n pi over Lx, and that means that the total solutions once per every value of n, tx are equal to an cosine n pi L over x times e to the minus n squared pi squared over L squared kappa t. Because remember, the u's are the products of the x's and the t's. All right. Well, now we need to write the total solution, which is the linear combination of all the possible solutions. All right, so we can write now the total solution as the sum of all the possible solutions that we got. One from the case lambda equals 0, and two different sets of infinite number of solutions for the case where lambda is less than 0. Now, let's tweak this one a little bit to make it look more familiar. Let me write u0 of tx as a0 over 2, right? This is an arbitrary constant, so an arbitrary constant over 2 is an arbitrary constant, so I can do that. I call the first one a tilde and this one a0 over 2, all right? Because it's just an arbitrary constant. If I do that, let's add all the solutions we found and find the total solution before imposing the initial condition. U of tx is the one that we found from lambda equals 0, a0 over 2, plus, this is just convenient to have it, as you will see. This set of infinite solutions, sum all of them. You have to sum the infinite number of them in general for the general solution. N equals 1 to infinity of an cosine n pi over L x times the t that I have here, e to the minus n squared pi squared over L squared kappa t. All right, plus the other infinite set of solutions that I found, which is all of them summed, n equals 1 to infinity, bn sine of n pi over L x, just put the parentheses, e to the minus n squared pi squared divided by L squared kappa t. Well, nice. This is the solution to the heat equation on the ring, periodic boundary conditions, compatible with the periodic boundary conditions just in a ring, but now we need to impose the initial condition to find the particular one that satisfies that initial condition, that is a distribution of temperature is some f of x. Well, here's the beautiful part, the way you see where the two comes in handy. You may have seen it already, of course. Impose the initial condition, which is u of 0x equals f of x. All right? So how do we find, so why is that? Imposing the initial condition will determine the constants, the a0, the an, and the bn. Okay, all of them, the infinite number of constants, we get the value of them. How? Well, let's impose it. So we write here u of 0x, so let's substitute by 0, wherever I see a t, I get a0 over 2 plus sum n equals 1 to infinity. Oh, not infinity. Infinity. an cosine of n pi l x times 1 plus sum n equals 1 to infinity bn sine n pi l x times 1, because t is 0, equals to f of x. Ha 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 ha! Right. The a0, the an, and the bn's is the coefficients of the Fourier series, the full range Fourier series on the period L to minus L, so it's a period of 2L of the function f of x. We don't need to extend it because it's already made periodic by the periodic boundary conditions. So yeah, the reason I wanted to add the 1/2, which is arbitrary here, is to make it look exactly like the Fourier series we have. So to find the f of x, well, in an exercise, f of x would be something concrete. In general, well, we know what it is. A0 is equal, so again, the period, it's 2L, okay? So this is 2 over 2L, which is 1 over L, integral from minus L to L of f of x, and an, it's equal, again, 2 over 2L, so 1 over L, integral from minus L to L, dx f of x cosine of omega x, or m pi L x, and finally, the bn's are 1 over L minus L to L dx f of x sine n pi over Lx. After computing these coefficients, you substitute in here, and that would be the final, so the complete solution to the equation. All right? That satisfies that initial condition and the periodic boundary conditions. Now, of course, in an exercise, it might be that I'll give you an f of x that by inspection, you can already tell what the Fourier coefficients are, same as we did before, okay? If that's the case, well, it's just much easier for you, but in either way, in either case, all that you need to do is get this function and do these integrals, which in general is not very difficult if the functions are simple, and they will be simple if I give you an exercise. Anyway, I think we've seen a bunch of examples and techniques to solve the heat equation. In the next video, we're gonna do the wave equation. So I'll see you there. Thank you for your patience. This is a long one. I hope that you enjoyed it. At least you have now the luxury of being able to pause it and continue a different day. See you in the next video.